If problem seems bigger and solution seems impossible and hope feel distant, here is the key. Change your mindset. It is the most powerful tool in your hands. It shapes how you see the problem and how you respond to them. You have the power to reframe it. Your job is to take the next step in front of you. You begin to realize that the solutions are working not against you, it's working for you, guided by the caring people who wants nothing but the best of you through this video. So here is the topic, that is group theory, and two problems are flashing on the screen which are very very important and most easiest problems. See here, the first problem is, if G is a set of even integers, see this is a set of all even integers, then prove that G is an abelian group with usual addition as the operation. So we have found the algebraic structure. G is the set of even integers and addition is an binary operator, and G plus is an algebraic structure. We have to show that G is an abelian group. So in order to show it's an abelian group, we have to prove five properties. One is closure, associativity, identity, inverse, and commutative law. And the next question here is, the set of Q plus of all the positive rational numbers form an abelian group under the composition defined by circles such that A circle B is equal to AB by 3 for every A comma B belongs to Q plus. Here Q plus is a set and circle is a binary operator. Then Q plus comma circle, we have to show that it's a abelian group. So through this composition, that is A circle B is equal to AB by 3. So let's start the question here. Question number 1. If G is a set of even integers, see here what is given. G is the set of even integers. And here the binary operator here is the plus. Therefore, G plus. So we have to show that, to prove that G plus is an abelian group. So which group it is? Abelian group. In order to show it's an abelian group, so we have to show the property, the first property here as closure law. So we have to show closure property. So for taking a closure property, we have to take two elements from the set G, that is, let A is equal to 2x, so which is an even integers which belongs to G, and B is equal to 2y, which again belongs to the set G as multiples of 2 is an even integer. So here is the binary operator, that is A plus B. So here this is 2x plus 2y. So if you take x common, that is x plus y here, for every x comma y belongs to set of integers. So here this is 2 into something. Therefore, if x belongs to z, y belongs to z is an integer, then x plus y is again an integer, and therefore this belongs to G. Therefore, A belongs to G, B belongs to G implies A plus B belongs to G, and therefore G is closed. Therefore, G is closed under addition. So the first property is true. And the next one is associative property. The next property here is associative property. So for the associative property, we have to take three elements. So I am taking three elements, that is, let A is equal to 2x, B is equal to 2y, and C is equal to 2z. For every x comma y comma z, z belongs to capital Z. So this is set of integers. Therefore, A belongs to G, B belongs to G, and C belongs to G as 2x, 2y, 2z are the set of integers. So now addition is the binary operator, and therefore I am starting with A plus B plus C. See here, what is A here? This is 2x. B here is 2y, and this is 2z. So here if I take 2 common, this will be x plus, this is y plus z. And therefore this is 2 times of this can be interchanged as x plus y plus z, as these are the set of integers. And therefore if I send 2 inside, this is 2 into x plus y plus this is 2z, and therefore this can be written as 2x plus 2y plus this value is 2z. So this is A plus B plus C. So I have started from this one and I have shown this one. Therefore A plus B plus C is equal to, this is A plus B plus C. For every A comma B comma C belongs to G, and therefore G is associative. G is associative. And the next property which I am going to show is identity. So for identity law, I have to take one element, that is A. Let A belongs to G. Let A is equal to 2x, which belongs to G. Then there exists 0 belongs to G such that, so we have to show A plus 0 is equal to, that is 2x plus 0, that is 2 into, this can be written as 2 into 0. So if I take common, this will be x plus 0, so which is equal to 2x, which is equal to A. Similarly, therefore, A plus 0 is equal to A, which is equal to 0 plus A. And therefore, 0 is the identity element. 0 is the identity element in G. And next one is, we have to show inverse property. So in order to find the inverse property, see here, what is the additive inverse for A? Let A belongs to G. So A is equal to 2x belongs to G. Then there exists minus A belongs to G such that A plus minus A is equal to 0 is equal to, this is minus A plus A. We have to show this. And therefore, A is equal to 2x, which belongs to G. Then there exists minus A is equal to minus AX belongs to G such that, so I am taking the addition for this. That is A plus of minus A is equal to, this is 2 plus of, this is minus 2x. So if I take 2 common, this will be x plus of minus x, and this is nothing but x minus x, which is equal to 2 into 0, which is equal to 0. And therefore we got A plus of minus A is equal to 0 is equal to minus A plus A for every A belongs to G. For every A belongs to G. Therefore, minus A is the inverse element. See here, this is the inverse element in G. Clear? And next property here is a commutative law. So we have to show a commutative law. So for commutative law, every time we have to take two elements. Let A is equal to 2x belongs to G, and small b belongs to 2y, which belongs to G. For every small x, small y are the set of integers. And therefore, if I take addition, that is A plus B, so this will be 2x plus 2y. If I take 2 common, this will be x plus y. So this can be written as y plus x, so which is equal to, this is 2y plus 2x, so which is nothing but b plus a. Therefore, a plus b is equal to b plus a. So which is a commutative. Therefore, G is commutative. So I have shown all the properties, all the 5 properties, and therefore we conclude that G plus, see here, G is a set of integers and plus is a binary operator, is an abelian group. So this is an abelian group. So let me explain you once again. See here, first thing is we have to show this is a closure law. So in order to show it's a closure law, we have to take two elements, so which are of the form of even elements, that is A plus B. So which is again an even element, so which belongs to G. Here A belongs to G, B belongs to G, implies A plus B belongs to G, and therefore G is closed under addition. So coming to associative law, A, B, C are taken from the set G, and I have started from A plus B plus C, and I have shown that A plus B plus C. So here G is associative. And next one here is an identity law. So in order to show it's an identity law, I have taken A is equal to 2x, which belongs to G. Then there exists 0 belongs to G, such that I have to show A plus 0 is again equal to A. That is 2x plus 0, which is equal to A. And therefore A plus 0 is equal to A is equal to 0 plus A. And therefore we conclude that 0. See here, 0 is an additive element. And next one, inverse law. So if A belongs to G, then there exists minus A belongs to G, such that A plus of minus A is equal to 0 is equal to minus A plus A. So we have to check whether it is equating to 0. A plus or minus A, that is 2x plus minus 2x. If I take 2 common, this is x minus x, which is equal to 0, and therefore minus a is an inverse element, and therefore commutative law, if a is equal to 2x and b is equal to 2y, so which belongs to G. I have started from a plus b and I have shown it is b plus a, and therefore G is a commutative, and therefore after fulfilling all the 5 properties, I say that G plus algebraic structure is an abelian group. And next one, what is the second question here? The second question is the set Q plus of all the positive rational numbers form an abelian group. And see here, so this is also so simple. The set Q plus of rational numbers form an abelian group. And now we have to start with this. So what is the set here? Q plus. And what is the binary operator? Circle. To prove that it is an abelian group. So in order to prove it's an abelian group, so we have to show all the 5 properties here. The first property which I'm going to show is a closure law. So what is this one? This is closure law. So I have to take 2 elements and I have to show it's a closure law. So here, for showing this one, A circle B is defined as AB by 3. So please remember this one. So A is a element from a rational number, b is an element from a rational number. So if I multiply also, it will be a rational number. So if I divide by 3 also, it is a rational number, and therefore this can be written as a circle B belongs to Q plus. So here if you observe this one, A belongs to Q plus, B belongs to Q plus implies a circle B belongs to Q plus, and therefore Q plus is closed under circle. So it is closed under circle. And next one is associative law. Associative law. So in an associative law, we have to take 3 elements. Associative law, we have to take 3 elements. See here, I am taking 3 elements as consider A circle, B circle, C. So let A comma B comma C belongs to, this is Q plus. So consider A circle, B circle, C. So if there is a circle operation, so what is the condition here given? That is A circle B is given as, see here, A circle B is given as AB by 3. We have to multiply both the elements and we have to divide by 3. And therefore, if I consider this circle, so what I'm going to do here, A circle, so this can be written as, we have to multiply both the terms and we have to divide by 3. And here I'm using this circle operator, and here also in this case also I'm going to multiply these two, and again I'm dividing by 3 here. So this will be A, B, C by 3 3s, this is 9. And again if I start with A circle B circle C. See here, A circle B circle C. Now I am going to use this operator, that is circle, in the brackets. So this will be AB by 3 circle C. So if I use the circle operator, now we have to multiply these two and divide by 3. And therefore this is AB by 3 into C. So I am going to multiply these two terms and again I am dividing by 3. So this will be again ABC by 3 3s are 9, and here also ABC by 9. So if you observe these two, this is ABC by 9 and this is ABC by 9, and this is A circle B circle C value, and this is A circle B circle C value, and both the values are same, and therefore we say that A circle B circle C is equal to A circle B circle C, and therefore Q plus comma circle is associative. This is associative. Clear? So I have shown its closure, it is associativity, and next one I am going to prove it's an identity law. Identity law also satisfies. So identity. For identity law, what we have to show, see here, as A belongs to Q plus, and there exists E belongs to Q plus such that, so what is the condition here? That is A circle E is equal to again A, which is equal to E circle A. Clear? And see here, if I equate A circle E to A, so if I use the operation. So this is what is the given condition here. A circle B is equal to, we have to multiply these two and again we have to divide. So if I apply this one, so I am going to multiply these two and again I am going to divide by 3. So if I cancel A here, then E is equal to 3. So in this case, E is equal to 3 is the identity element. So we got the identity element. Therefore, E is equal to 3 is the identity element. And next one, we have to show inverse law. So in order to show inverse law, for inverse law, see here, if A belongs to Q plus, then there exists B belongs to Q plus such that, so what is the formula here? A circle B is equal to identity element. Then we say that B is the inverse of A, which is equal to B circle A. So I'm going to use this one, that is A circle B is equal to E. So this case I'm using, so according to our definition, if there is a circle operator, A circle B is nothing but AB by 3, it is given in the question. And therefore I'm writing that is AB by 3 and E is already found as 3. And therefore AB is equal to 9. 3 3 is the 9 and B is the inverse of A. And therefore B is equal to 9 by A. And therefore for each and every element A by 9 by A. So here 9 by A is the inverse element of A. So the inverse element of A. And we got the inverse element for this. And the last thing here is commutative law. So here commutative law. For commutative law, we have to consider two elements. So one is, so A belongs to Q plus, B belongs to Q plus, and now we have to start with A circle B. So A circle B is equal to AB by 3. This can be transformed as BA by 3 and according to our circle operator, we can write this as B circle A. And therefore, A circle B is equal to B circle A. Therefore, Q plus comma circle is commutative. So I have satisfied. So Q plus comma circle satisfied all the 5 properties and therefore Q plus comma circle is an which group? It is an abelian group. So in order to show it's an abelian group, we have to prove 5 conditions. The first one is a closure law. So closure law is nothing but if A belongs to Q plus, B belongs to Q plus implies A circle B belongs to Q plus and therefore Q plus is closed in the circle. For associative law, we have to take 3 elements and we have to use this circle operator and therefore A circle B circle C value is ABC by 9 and A circle B circle C value is also ABC by 9 and therefore this is associative. So this is Q plus comma circle is associative. And next one is an identity law. So according to the identity law, we have to take one element that is A belongs to Q plus and we have to show that A circle B is equal to A and therefore AE by 3 is equal to A and we got the identity element as 3. For the inverse element here, A circle B is equal to A, we have to find out the B value here. B value is 9 by A for every element. 9 by A is an inverse element of A. We got the inverse element for each and every element. And next one is the commutative law. Here I have started with A circle B and I have shown B circle A and therefore it is commutative. And after satisfying all the 5 conditions, that is closure, associativity, identity, inverse and commutative law, we say that Q plus comma circle is an abelian group. This is how we have to check all the 5 properties in order to show it's an abelian group. And therefore I am going to post so many problems related to this series and definitely it will be very helpful for your preparation. Go through this video for one more time if you don't connect for first time, and if you really understand, please raise your thumb, pass it on to your friends and share it with as many friends as you can, and that will be the greatest help to this channel. Support this channel and spread the knowledge. Thank you so much for staying till the end.